This lecture is part of an online course of multivariable calculus, and I'm going to talk about 3 useful parameterizations that we use for parameterizing the curves in line integrals. So let me start. The first one is parameterization parametric equation of a circle of radius r. Okay, so if we have a circle of radius r, we can actually use polar coordinates for that, and I'm gonna say that x of t is equal to r cosine t and y of t is r sine of t. And pay attention that r here is just basically a number, so it's just a constant, so the parameter that we have would be just t. This is just the number, and then based on the equation that part of the curve that is given to you, for example, if you have the full circle, so for the full circle, theta, or actually t, should be between 0 and 2 pi. If we just have a half circle, top half of the circle, then t is basically between 0 and pi, and it depends basically where we have different parts of the curve. The second one is parametric equations of the line segment from the point A to the point B. Okay, so assume that we have this line segment in here that we want to find its parametric equation. So how do we do that? There are 2 ways to do it. The first one is to using the vectors, and I say that I have a vector from A to B, then I can say that equation for this vector would be the first point plus the parameter t, the difference between the second point minus the first point, b minus a. Okay, so this is basically what? Basically I have a and b plus t, then the first coordinate, difference between the first coordinates, and then the second coordinates. Okay, so I get what? I get a plus t, c minus a, and b plus t, d minus b. Okay, let me use this notation that we use for vectors. And so I can say that x of t is equal to a plus t c minus a, and y of t is b, oops, I made a mistake in here. No, that's correct. b plus t d minus b. Okay, and then in that case the parameter t is between 0 and 1. I don't suggest that you memorize this. I suggest that you memorize that. The first point plus t, the difference between the first and the second point, and then t is between 0 and 1. Why is that? Plug in t equals to 0 in here, then this part would be 0. I just get a. So at the time t equals to 0, we are here. Plug in t equals to 1, I get a plus 1, b minus a. A and negative a would be cancelled, so I left with a b, which would be the second point in here. Okay, so this is the first way to write line segments from A to B. There is another way to do it. This is the first way. The second way to do it is to basically write equation for the line. Right? Equation of the line. Well, how do we do that? Well, we say that y is equal to y minus, pick a point. Actually, we need one slope. Let me write it like that. We need a slope and we need a point on the line. Point on the line. The point, I'm going to choose A and B, the point A. And the slope would be the difference between the y coordinates, which would be d minus b, and then over the difference between x coordinates, c minus a. And so equation of the line would be y minus b is equal to the slope x minus a. Okay, so now this is not still parameterized. To parameterize that, I need to say, let's take x to be my t and y to be g of t. What is g of t? Bring negative b on the other side, and then it would be d minus b over c minus a, the slope x minus a, and plus b. And x was just t. The rest are just numbers. Okay, so again, you don't need to memorize any of them. You just say that you need to write equation of the line and then let x to be t and then y to be g of t. The rest, right? Okay, very good. Now t is going to be from A to C. You see, that's because x is from A to x coordinate is just basically from A to C. That's why the parameter is between A and C. This is the second way. And then the third equation that we are gonna parameterize would be this one, parametric, oops, number 3 actually. So we're gonna write parametric equation for the function y equals to f of x. Okay, so for that, just let x to be the parameter t and y to be f of t. Now I'm gonna solve this example. Write parametric equation of the curve C consisting of curve C1, which is part of the parabola y equals to x squared from 0, 0 to 1, 1, followed by the vertical line segment C2 from 1, 1 to 1, 2, and then calculate the line integral. So let me graph the region of my integration first. So I'm gonna, oops, no, I'm gonna have x and y axis. So the curve C consists of two parts. Part of the parabola y equals to x squared. So this is that from 0, 0, oops, to 1, 1. So this is 1, 1. The point 0, 0, the point 1, 1 is right there. So the direction of the curve is like this. And then I have the line segment from 1, 1 to 1, 2. So just assume that this is the point 1, 2. That is the point 1, 1. So this part in here is C2. So this is C1, this is C2. Together would be the curve C. So let me parameterize C1 first. So C1 has the equation y equals to x squared. As we discussed, we can let x to be parameter t and then y to be t squared. Okay, and in that case, since x should be from 0 to 1, I'm gonna let t to be from 0 to 1, and then you can just check. Plug in t equals to 0, I get 0, 0, which is good. Plug in t equals to 1/2, I get 1/2, 1/4, which is somewhere in here. And then plug in t equals to 1, I get 1, 1, which is right there. So it's a good parameterization. How about C2? C2 is the line segment. So it's a line segment from 1, 1 to the point 1, 2. Okay, for equation for the line segment, I can parameterize it like that. The first point plus t times the second point minus the first point. Okay, where t is between 0 and 1. Okay, so let me basically simplify that. I get 1, 1 plus t. 1 minus 1 is 0. And then 2 minus 1 is just 1. So I get 1 plus 0t and 1 plus 1t, right? So this is 1 and 1 plus t. This is the first coordinate, 1, and then y of t to be 1 plus t, where t is between 0 and 1. Okay, so we can use this parameterization for this line segment, or I can say that this is part of the line x equals to 1. So this is the line x equals to 1. So I'm gonna let x to be 1 and y to be t, and in that case t is from 1 to 2. Just because I want to be from 1, 1 to the point 1, 2. Okay, so I can use this parameterization in here, this one, or I can use this one. Yeah, both of them would work. And actually the line integral does not depend on the parameterization, so I can use any of the parameterizations. So now let me use the parameterization to solve this line integral. So what do I have? I have the integral of 2x dx over the curve C. Since the curve C consists of two parts, C1 plus C2, I can find 2x dx on C1, and then I add it to 2x dx on C2. Okay, so let's calculate each one of them. So the integral of 2x dx C1 is what? Parameterization for C1 was t and t squared, t between 0 and 1. So it was t and t squared. Okay, so the integral would be equal to what? 2. Instead of t, I need to put the parameterization for x, which is t, and then ds. I'm sorry, that's my mistake. It's with respect to arc length, ds. Okay, so this is ds, and for ds I have what? The formula for speed. Derivative of this square, so this is 1 square plus derivative of this t square. This is the parameterization for C1, so it should be t square. Okay, and derivative of that would be 2t square, and then dt, and then on the parameterization t from 0 to 1. Okay, that's good. I need to solve this problem. So let me simplify that. I have a square root of 1 plus 4t squared. I can use u sub, and I said u to be 1 plus 4t squared. Du is 8t dt. Okay, now let's plug in everything into the integral. I'm not going to change the bounds. So I have a 2, and then t times dt would be what? T times dt would be du over 8. So I have du over 8, and I have square root of, this is my u, square root of u. Okay, so let me simplify that. I get 1/4 that I bring it out, and then the integral of u to the power of 1/2 du. So it would be 1/4 u to the power of 1/2 plus 1 divided by 1/2 plus 1. Okay, now let me replace u with 1 plus 4t squared to the power of 3 inside the square root divided by 3 over 2, and then t is from, it's given from 0 to 1. Okay, so 1/4, and then multiply by 2 over 3. I'm just gonna bring 3 over 2 on top, so I get 2 over 3, and then I get square root of 1 plus 4t squared to the power of 3 from 0 to 1. Plug in 1, I get 1 over 16 here because the 2 and 4 would be cancelled. Plug in 1, so I get square root of 5 to the power of 3 minus, plug in 0, I get square root of 1 to the power of 3, which is basically 1. Okay, so this is the answer for the integral of 2x ds over the curve C. Now let me calculate the second one, this one, using these two parameterization. Okay, so I have the integral of 2x ds over C2. Okay, I'm going to use the first parameterization. Let me go up, which is 1 plus t between 0 and 1. Okay, so this is 1, and then 1 plus t, and t was between 0 and 1, so 2. Instead of x, I put my parameterization, which is 1. ds would be the formula for speed. Derivative of this is 0, so I get 0 squared. Derivative of that with respect to t is 1, so I get 1 squared, and then dt. So this is just 1. The answer here is just 2, so I get 2t. Let me write everything together, it's just 2. So let me not skip any step. So I have 0 to 1, 2 dt, which would be 2t, from 0 to 1, which is just 2. I can use the other parameterization, which was what? The other one that we discussed is 1 and t between 1 and 2. Let's see what we get. So this one is 1 and t, and then t was between 1 and 2. Why it was between 1 and 2 is just because we wanted to go from this point to that point, and the parameter t is the second coordinate. The second coordinate is between 1 and 2. That's why t is between 1 and 2 here. Okay, so 2, again, the first parameterization is just 1, and then ds is what? Is dx dt squared plus dy dt squared, just as a recall. Dx dt squared would be 0, plus dy dt squared is just 1 squared dt. You see, it's exactly the same. Between 1 and 2, it would be 2 dt, which would be 2t between 1 and 2. So I get 2 times 2, which is 4, minus 2 times 1, which is 2, and the answer is 2. The same thing. So now the integral of 2x ds over the curve C, which was the integral of 2x ds over C1, plus the integral of 2x ds over C2 is, what was the first one? Is this one, which is 1 over 6, 5 root 5 minus 1, plus this one in here is just 2. Okay, and as you see that these two are the same. with different parameterizations, we get the same answer for the line integral.